Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe the day has been long, maybe your thoughts have been racing, or maybe you simply crave the gentle comfort of ocean mysteries whispered softly into the dark. Whatever brought you here, you've arrived at exactly the right place. Tonight you have nothing to do but rest. Let your breathing slow, let your muscles soften, let gravity pull you gently down into comfort as we descend together into one of Earth's most profound secrets. We're going to journey to the deepest place in all the world's oceans, a place so remote, so dark, so impossibly far beneath the waves that more humans have walked on the moon than have seen it with their own eyes. We're traveling to the Mariana Trench, and within it, to a point called Challenger Deep, where the ocean floor drops away to depths that challenge everything we think we know about life, pressure, and the very limits of our planet. Tonight's voyage will be slow and gentle. We'll drift down through layers of darkness, past depths where sunlight fades to nothing, through pressures that would crush almost anything, into cold that hovers just above freezing. And yet we'll discover that even in this most extreme environment, life persists in forms both strange and beautiful. We'll meet creatures that glow in the blackness, organisms that thrive where nothing should survive, and landscapes carved by forces operating over millions of years. Some of what you hear tonight might surprise you. Other parts might lull you into that perfect space between waking and dreaming. That's exactly as it should be. The deep ocean has always been a place of mystery, and the Mariana Trench is its most mysterious heart. As we explore together, let your mind wander where it wishes. If sleep finds you halfway through our journey, welcome it. The abyss will still be there, patient and unchanging, waiting in the dark. And just before we begin our descent, if these calm explorations help you unwind at the end of your day, if they give you a quiet refuge from the noise of modern life, consider subscribing to Deep Sleep Seas. Each video is crafted to blend scientific wonder with the peaceful rhythms that help carry you toward rest. By subscribing, you help others discover this channel too, one sleepy soul at a time, all of us drifting together through the ocean's deepest mysteries. Now let's begin our journey down past the surface waves, down past where light can reach, down to where the pressure becomes almost unimaginable and the cold never changes, down to the very bottom of the world, to see what waits there in the ancient, patient darkness of the Mariana Trench. The Mariana Trench lies in the western Pacific Ocean, about 200 kilometers east of the Mariana Islands, not far from Guam. If you could drain all the water from the Pacific and stand at its edge, you would see something that looks less like a simple valley and more like a wound in the earth itself. A great crescent-shaped scar, curving through the ocean floor for more than 2,500 kilometers. That's over 1,500 miles of continuous depression, a gash in the planet's crust that's been forming for millions of years. From above, if you could see through all that water, the trench would appear as a narrow, curving line. It averages about 69 kilometers in width, roughly 43 miles across, not particularly wide, considering its length. But what makes the Mariana Trench extraordinary, what sets it apart from every other place on Earth, is not its length or its width. It's the depth, the absolutely staggering, mind-bending depth. At its deepest point, a place we call Challenger Deep, the ocean floor plunges down nearly 11,000 meters beneath the surface. That's approximately 36,000 feet, or about 6.8 miles straight down. To put that in perspective, imagine standing at sea level and looking up at Mount Everest. The mountain rises about 8,849 meters above sea level. Now flip that image. Drop Mount Everest into the Mariana Trench at Challenger Deep, and the summit of the world's tallest mountain would still be covered by more than 2 kilometers of water. More than a mile of ocean would stretch above Everest's peak before breaking the surface. Think about that for a moment. The deepest part of the ocean is deeper than the highest mountain is tall. It's a comparison that helps us grasp something so extreme, it almost defies imagination. We can see mountains. We climb them, photograph them, understand their scale by standing at their base and gazing up. But the Mariana Trench hides beneath miles of dark water, invisible, inaccessible, known only through the instruments we've managed to send down into its depths. The trench was formed by a process that's still happening today, right now as you rest and listen. It's called subduction, and it's one of the most powerful geological forces on the planet. Earth's crust is not a single solid shell. It's broken into massive pieces called tectonic plates, and these plates are always moving, drifting slowly across the more molten layer beneath them. Where two plates meet, extraordinary things can happen. At the Mariana Trench, the Pacific Plate, one of the largest tectonic plates on Earth, is colliding with the smaller Mariana Plate, but they're not crashing together like cars in an accident. Instead, the Pacific Plate is sliding beneath the Mariana Plate, diving down into the Earth's mantle in slow motion. This downward bend, this descent of one plate beneath another, creates the trench. As the Pacific Plate dives, it drags the edge of the overriding plate down with it, forming that deep V-shaped depression we call the Mariana Trench. The Pacific Plate at this location is old, some of the oldest oceanic crust on Earth, approximately 170 million years old. Old oceanic crust is cold and dense, heavier than the younger crust around it. That density helps it sink, helps it slide down beneath the lighter Mariana Plate, and as it descends it bends, creating that slot-shaped valley at Challenger Deep, the absolute deepest point. This process is not peaceful. The grinding of plate against plate generates earthquakes, hundreds of them. Over the past 50 years, scientists have recorded earthquakes ranging from 4.5 to 8 on the Richter scale in the deepest parts of the world's oceans. Each time the plates shift, even slightly, the fine sediment covering the seafloor gets kicked up and slowly settles back down, creating a smooth blanket over the bottom. That's why, when explorers have finally reached Challenger Deep, they've found the floor surprisingly smooth, covered in a layer of fine ooze that looks almost undisturbed. The movement of these plates is also indirectly responsible for the Mariana Islands themselves. As the Pacific Plate descends into the mantle, the rock begins to melt. Water trapped in the minerals of the subducting plate is released, and this water causes the overlying mantle to melt as well. That molten rock, lighter than the solid rock around it, rises up through the Mariana Plate and erupts at the surface as volcanoes. Over millions of years, those volcanic eruptions built the chain of islands that gives the trench its name. The Mariana Trench is not a fixed, unchanging feature. It's dynamic, active, still being shaped by the same forces that created it. Every day, every year, the Pacific Plate continues its slow dive into the Earth. The trench grows slightly deeper, shifts slightly in position, changes in ways too subtle to measure over human lifetimes, but profound over geological time. It's been doing this for at least 50 million years, and it will likely continue for millions more, a reminder that our planet is not solid and static but fluid and alive, constantly remaking itself through processes that dwarf human timescales. Far from any major landmass, far from the mouths of muddy rivers, the Mariana Trench has remained relatively free of sediment. Other deep trenches around the world are filled with debris washed down from continents, layers of mud and sand that make them shallower. But the Mariana Trench lies in the open ocean, remote and isolated. The only things that fall into it are the slow rain of organic matter from the surface and whatever creatures or minerals drift down through the water column. This lack of filling, this relative emptiness, is part of what makes it so deep. And nearby fault lines cut the Pacific Plate into a narrow tongue at the site of the trench, allowing the plate to bend more steeply downward than at other subduction zones. This particular geometry, this specific arrangement of geological forces, conspired to create the deepest natural point on Earth's surface. Not the longest trench, not the widest, but the deepest. The place where gravity and geology have carved the most profound wound into our planet's skin. As you rest, imagine that immense depth. Imagine the weight of all that water pressing down. Imagine the darkness, absolute and total, that fills that vast space. The Mariana Trench is not just a hole in the ocean floor. It's a portal into deep time, a window into processes that shape continents and oceans, a place where the rules of life on the surface no longer apply. And tonight we're going to descend into it, slowly and gently, to see what secrets it holds. To understand the Mariana Trench, we need to understand what happens as we descend from the surface. The ocean is not uniform. It's layered, like a cake, with each layer having its own character, its own temperature, its own amount of light. And as we move deeper, everything changes in ways that seem designed to test the very limits of what life can endure. At the surface, where sunlight sparkles on the waves, the ocean is warm and bright. This is the epipelagic zone, the sunlight zone, where most of the ocean's life concentrates. Here in the upper 200 meters, enough light penetrates for photosynthesis to occur. Phytoplankton drift in the currents, forming the base of the ocean's food web. Fish swim in vast schools. Marine mammals surface to breathe. This is the ocean we know, the one we can see and swim in, the one that seems familiar and almost friendly. But as we descend past 200 meters, the light begins to fail. We enter the mesopelagic zone, the twilight zone, where only the faintest blue light filters down from above. This is a realm of shadows, where many creatures possess large eyes to capture every photon, where bioluminescence becomes common as animals create their own light through chemical reactions in their bodies. The twilight zone extends down to about 1,000 meters, and in this space the temperature drops steadily. The water grows colder with every meter of depth. At 1,000 meters, the twilight fades completely. We've entered the bathypelagic zone, the midnight zone, and from here down to about 4,000 meters, there is no natural light at all. None. The darkness is absolute and permanent, broken only by the occasional flash of bioluminescent creatures communicating, hunting, or trying to confuse predators. The water temperature here hovers just above freezing, rarely rising more than a few degrees Celsius. The pressure has increased to about 100 times what we experience at the surface. For every 10 meters we descend, the pressure increases by about 1 atmosphere. At 1,000 meters, we're experiencing about 100 atmospheres of pressure. Below 4,000 meters, we enter the abyssopelagic zone, the abyssal zone, which extends down to about 6,000 meters. The pressure here is crushing, more than 600 times surface pressure. The temperature remains constantly cold, between 1 and 4 degrees Celsius. The water is calm, undisturbed by surface storms or tides. In this zone, the bottom of the ocean is still far below. We're deeper than most of the ocean floor, but we haven't reached the trenches yet. This is where most of the deep ocean exists, a vast, cold, dark plain that covers more of Earth's surface than all the continents combined. And then, past 6,000 meters, we descend into something else entirely. We enter the Hadalpelagic zone, named after Hades, the ancient Greek underworld. The Hadal zone is defined as any part of the ocean deeper than 6,000 meters, and it exists only in the trenches. Less than 1% of the ocean floor lies at Hadal depths. These are the deepest, most extreme environments in the entire ocean, and the Mariana Trench contains the deepest point of them all. At the bottom of Challenger Deep, about 11,000 meters beneath the surface, the water pressure is staggering, approximately 1,086 bar, or about 15,750 pounds per square inch. To put that in terms that might mean something, imagine an African elephant standing on your thumbnail. That's roughly the pressure at Challenger Deep, or think of it this way, 8 tons of pressure on every square inch. The weight of the entire water column above pressing down with a force that would instantly crush any creature not specifically adapted to withstand it. Your bones would literally dissolve under that pressure. The air spaces in your body would collapse. Any submarine not specifically designed for these depths would implode like a crushed soda can, metal buckling inward faster than the human eye could follow. This is why so few have been to the bottom of the Mariana Trench. The engineering challenges are immense, the dangers profound, the margin for error essentially zero. The temperature at the bottom is just 1 to 4 degrees Celsius, hovering perpetually just above freezing. The saltiness of the water prevents it from freezing solid, but it's as close to ice as liquid water can get at that depth. This cold is constant, unchanging, unaffected by seasons or weather. At the surface, the ocean's temperature might vary by many degrees throughout the year. At the bottom of the Mariana Trench, it never changes. It has been this cold for millions of years, and it will remain this cold for millions more. The darkness is total. Not a single photon of sunlight has reached this depth since the trench formed. The only light that exists here comes from bioluminescent creatures, and even those are rare in the deepest parts. Most of the time, most of the space, there is simply nothing but blackness. A darkness so complete that human eyes, adapted for detecting light, would find no difference between eyes open and eyes closed. There is nothing to see, nothing that could ever be seen without bringing artificial light down from the surface. And yet, despite all this, despite the crushing pressure, the bone-chilling cold, the absolute darkness, life exists in the Mariana Trench. Not just microbes, though they are certainly there, but complex animals, fish with translucent bodies, amphipods the size of dinner plates, single-celled organisms the size of your fist, creatures that have adapted to conditions that seem designed to forbid life entirely. They don't just survive here, they thrive, filling ecological niches, hunting and being hunted, living out their lives in a realm so extreme we can barely comprehend it. The Hadal Zone, the deepest layer of all, is one of the least explored habitats on Earth. More humans have walked on the Moon than have descended to Hadal depths. We've sent more missions to Mars than to Challenger Deep, and yet it covers a significant area of our planet's surface. The trenches might be narrow, but they're long, and when you add up all the Hadal zones in all the trenches around the Pacific and elsewhere, you're talking about an area comparable to the size of Australia. An entire continent-sized habitat that we've barely begun to explore, barely started to understand. As you rest tonight, imagine that descent. Imagine the light slowly fading from blue to twilight to absolute black. Imagine the pressure building, the cold intensifying, the surface world receding farther and farther above until it might as well be on another planet. The Mariana Trench is not just deep, it's alien, as foreign to us as any place in our solar system, and yet it's right here, on Earth, sharing the same ocean we swim in at the beach, separated from the surface by nothing but water, but that water might as well be the void of space for all that it allows us to visit easily. We are descending now, slowly and carefully, deeper with each breath you take, each beat of your heart, down through the zones, past the point where light fails, past where the pressure would crush anything soft, down toward the very bottom, where only the most extraordinary adaptations allow life to persist. Rest now, and let the descent continue. There is no hurry. The abyss will wait for us, patient as it has been for millions of years. To truly understand the Mariana Trench, we need to look back in time, millions of years, to when the forces that created it first began their work. The story of the trench is the story of plate tectonics, of the slow dance of continents and ocean basins, of rock and heat, and the inexorable pull of gravity. Earth's outer layer, the lithosphere, is broken into about 15 major tectonic plates and many smaller ones. These plates are not static. They float on the more molten plastic-like rock of the mantle beneath them, moving at rates measured in centimeters per year, about as fast as your fingernails grow. Slow by human standards, but given enough millions of years, these movements reshape the entire planet. Plates move because of convection currents in the mantle. Heat from Earth's core causes rock deep below to warm, become less dense and rise. As it rises, it spreads out beneath the plates, pushing them along. When the rock cools, it becomes denser and sinks back down, creating a circular flow. This convection, driven by the planet's internal heat, is what powers plate tectonics, and plate tectonics is what shapes the surface of our world. Where plates move apart, new crust forms as magma rises to fill the gap. This happens at mid-ocean ridges, underwater mountain ranges where volcanic activity constantly creates new seafloor. Where plates slide past each other, we get transformed faults, zones of earthquakes and grinding motion. And where plates collide, we get either mountains, as one plate crumples against another, or subduction zones, where one plate dives beneath the other. The Mariana Trench is a subduction zone, and a particularly dramatic one. Here, the Pacific Plate, the largest tectonic plate on Earth, collides with the much smaller Mariana Plate. The Pacific Plate is oceanic crust, made of dense basaltic rock that formed at a mid-ocean ridge. The Mariana Plate is also oceanic crust. When two oceanic plates collide, the older, colder, denser one typically subducts beneath the younger, warmer, lighter one. The Pacific Plate at the Mariana Trench is ancient, some of the oldest oceanic crust on Earth. It formed approximately 170 million years ago, during the Jurassic period when dinosaurs walked the land. That's how old some of the rock is, that's currently diving into the mantle beneath the Mariana Islands. For comparison, most oceanic crust is much younger, typically less than 200 million years old, because it's constantly being created at mid-ocean ridges and destroyed at subduction zones. The rock of the Pacific Plate at the Mariana Trench has been on Earth's surface for an immense span of time, but now it's returning to the mantle, being recycled back into the planet's interior. Old oceanic crust is cold and dense. It's had millions of years to cool down after its formation at a mid-ocean ridge. That density makes it negatively buoyant, meaning it wants to sink. When it collides with younger, lighter crust, gravity helps pull it downward. This is why subduction occurs. The Pacific Plate isn't being pushed under the Mariana Plate so much as it's pulling itself down, its own weight dragging it into the mantle, in a process geologists call slab pull. As the Pacific Plate descends, it bends. Imagine pushing a rigid board under the edge of a rug. The board can't just disappear, it has to bend downward. The same thing happens with the Pacific Plate. Where it bends, where it starts its descent into the mantle, the seafloor deforms. The overlying plate gets dragged down slightly, and the combination of the descending plate and the bending crust creates the deep, V-shaped valley we call the Mariana Trench. This bending and descent don't happen smoothly. The plates don't slide past each other like well-oiled gears. They stick and catch on each other, building up stress over decades or centuries. Then suddenly, they slip, releasing that accumulated stress in an earthquake. Some of the largest earthquakes ever recorded have occurred at subduction zones. The 2011 Tohoku earthquake in Japan, which generated a devastating tsunami, was a subduction zone earthquake. The 2004 Indian Ocean earthquake and tsunami, which killed over 200,000 people, occurred at a subduction zone off the coast of Sumatra. The Mariana Trench subduction zone is also capable of generating powerful earthquakes, though it's located far from major population centers, which means its earthquakes cause less damage. But they still happen regularly. Hundreds of earthquakes occur in the Mariana region every year, most too small to feel, but some large enough to shake the islands and generate small tsunamis. Each earthquake is a reminder that the plates are still moving, still grinding against each other, still driving the Pacific Plate down into the mantle. As the Pacific Plate descends, it doesn't just disappear. It goes down, down, down into the mantle, sinking through the upper mantle, past the transition zone at about 460 kilometers depth, and eventually reaching the lower mantle. Scientists have used seismic waves from earthquakes to image these descending slabs of oceanic crust, and they've found that some slabs go all the way down to the boundary between the mantle and the core, nearly 3,000 kilometers beneath the surface. The Pacific Plate beneath the Mariana Trench will eventually reach those depths too, over millions of years, slowly sinking through the solid yet flowing rock of the mantle. But as it descends, something else happens. The plate begins to dehydrate. When oceanic crust forms at a mid-ocean ridge, it's hot and interacts with seawater, which gets trapped in the minerals of the rock. As the crust ages and moves away from the ridge, it cools and water remains locked in its crystal structure. When that crust gets subducted, the increasing temperature and pressure squeeze the water out, forcing it upward into the mantle wedge above the descending plate. This released water is crucial. It lowers the melting point of the mantle rock above it. Normally the mantle is solid, too cool and under too much pressure to melt, but add water and the melting point drops significantly. The mantle rock begins to partially melt, forming magma. This magma, being less dense than the solid rock around it, rises. It rises through the Mariana Plate, pools in magma chambers beneath the surface, and eventually erupts as volcanoes. This is why volcanic arcs form parallel to trenches. About 200 to 300 kilometers from the Mariana Trench, there's a line of volcanoes running roughly parallel to it. These are the Mariana Islands, and the many submarine volcanoes that form the Mariana Volcanic Arc. They exist because of the water released from the subducting Pacific Plate. Remove the trench, remove the subduction, and the volcanoes would eventually go dormant. The two are intimately linked, different expressions of the same fundamental process. The subduction that creates the Mariana Trench has been going on for a very long time. The Mariana subduction system is part of the larger Isobonin-Mariana system, which began forming between 50 and 52 million years ago, during the Eocene epoch. That's shortly after the extinction of the dinosaurs, at a time when the first modern mammals were beginning to diversify. For over 50 million years, this system has been active, building volcanic arcs, generating earthquakes, creating trenches. The exact location and configuration have changed over that time, but the fundamental process has continued uninterrupted. About 6 million years ago, something interesting happened. The trench began to migrate westward, and a back arc basin began to open behind the volcanic arc. This is the Mariana Trough, a zone of seafloor spreading behind the islands. In essence, the overriding plate began to split, with the eastern part being pulled toward the trench and new seafloor forming in the gap. This created a complex three-part structure. the trench, the volcanic arc, and the back arc basin, all existing side by side, all active, all part of the ongoing tectonic dance. The Mariana Trench is not unique in being a subduction zone trench. There are many others around the Pacific Ring of Fire. The Japan Trench, the Peru-Chile Trench, the Aleutian Trench, and others. But the Mariana Trench is the deepest, and that's partly because of local factors. The age and density of the subducting Pacific Plate, the angle at which it descends, the lack of sediment filling it, and the particular geometry of nearby fault lines, all conspire to make this specific spot the deepest of all. It's not magic or mystery. It's geology, the result of specific conditions aligning in a specific place over millions of years. As you rest tonight, think about the forces at work beneath the Mariana Trench. Imagine the entire Pacific Plate, an area larger than all the continents combined, slowly moving westward, centimeters per year, driven by convection in the mantle. Imagine it reaching the edge of the Mariana Plate and bending downward, beginning its descent into the planet's interior. Imagine the earthquakes as the plates catch and slip, the volcanoes erupting far above as water is released from the descending slab, the slow, patient accumulation of millions of years of motion that carved the deepest wound in Earth's surface. It's happening right now, as you listen, as you breathe, as you drift towards sleep. The planet is alive, moving, remaking itself, and the Mariana Trench is one of the most dramatic expressions of that ongoing transformation. For most of human history, the depths of the ocean were as inaccessible as the stars. We could see the surface, sail ships across it, dive down a few meters if we held our breath. But the deep ocean remained utterly unknown. We didn't know what was down there, how deep it went, or whether anything could survive in such a place. The Mariana Trench in particular existed beyond the reach of any technology humans possessed for millennia. The first real attempt to measure the depth of the Mariana Trench came during one of the greatest scientific expeditions of the 19th century. The HMS Challenger, a British Royal Navy corvette converted for scientific research, set sail in 1872 on a voyage that would last almost 4 years and cover nearly 70,000 nautical miles. The Challenger expedition, as it came to be known, was the first major expedition dedicated to exploring the deep ocean, and it revolutionized our understanding of what lay beneath the waves. On March 23, 1875, the Challenger stopped in the western Pacific, southwest of the Mariana Islands. The crew began a depth sounding, a process that involved lowering a weighted rope down until it hit bottom. This was painstaking work. The rope had to be heavy enough to sink quickly, but marked so they could measure how much had been let out. As the rope descended, more and more was released, far more than the crew had anticipated. After a very long time, the rope finally went slack. They'd hit bottom. When they hauled the rope back up and measured it, they were astonished. The depth was recorded as 4,475 fathoms, about 8,184 meters, roughly 5 miles. This was far deeper than anything they'd measured before, deeper than anyone had imagined the ocean could be. They didn't know it at the time, but they'd found the Mariana Trench. Their measurement was not precise by modern standards, and they didn't reach the absolute deepest point, but they'd made the first human contact with one of Earth's most extreme environments. The discovery was important, but it didn't reveal much about what the trench was actually like. A rope tells you depth, but nothing else. No samples were collected from that particular sounding, no observations made. The bottom of the trench remained a mystery, known only as a number on a chart, a depth too extreme to truly comprehend. In 1951, another British ship, the HMS Challenger II, returned to the area. This time, they had better technology, echo sounding. Instead of lowering a weighted rope, they sent sound pulses down through the water. By measuring how long it took for the sound to bounce off the bottom and return, they could calculate depth much more accurately. During their survey, they found a depth of approximately 10,900 meters, about 35,800 feet. This spot, which they measured at about 11 degrees 19 minutes north, 142 degrees 15 minutes east, was the deepest point they found. They named it Challenger Deep, after both their ship and the original HMS Challenger that had first explored the region. For nearly a decade, Challenger Deep remained a dot on a map, a number representing a depth almost beyond imagination. Then, in 1960, 2 men decided to actually go there, not to send down an unmanned probe, but to descend themselves, in person, to see the bottom of the world with their own eyes. Lieutenant Don Walsh of the United States Navy and Swiss oceanographer Jacques Piccard climbed into a deep-sea submersible called the Trieste on January 23, 1960. The Trieste was a bathyscaphe, a type of vessel designed specifically for deep-sea descents. It consisted of a large tank filled with gasoline for buoyancy and a small spherical chamber for the crew, made of thick steel to withstand pressure. The descent took nearly 5 hours. Slowly, carefully, the Trieste sank through the zones of the ocean, through the sunlight zone, through the twilight, into the absolute darkness of the abyss. The pressure increased steadily. They could hear strange creaking sounds as the sphere compressed slightly under the growing weight of water. At around 9,000 meters, a small viewing port cracked. Nothing catastrophic, but unnerving. They continued anyway. At 10,912 meters, according to their instruments, they reached the bottom. Through the small viewing port, illuminated by their lights, Walsh and Piccard saw a featureless plain of fine sediment, grey-white ooze stretching away into the darkness. And to their great surprise, they claimed to see living creatures. Piccard reported observing a flatfish, about 30 centimeters long, swimming near the bottom. If true, this would have been proof that complex life could survive even at the deepest point on Earth. However, many marine biologists have since questioned whether what Piccard saw was actually a fish. At such depths, visibility through a small port in artificial light is poor, and it's easy to misidentify something. Most scientists now believe he probably saw a sea cucumber or some other bottom-dwelling invertebrate, not a fish. True fish, with swim bladders and other air spaces, would have difficulty at such depths. But whether it was a fish or something else, the observation confirmed that life existed in Challenger Deep. Walsh and Piccard spent about 20 minutes on the bottom. The cracked window made them cautious, and there wasn't much to do. They couldn't take samples. The Trieste wasn't equipped for that. They couldn't move around much. The sphere was tiny, barely big enough for 2 people. They could only look and take a few measurements. Then they dropped their ballast, heavy iron pellets that had been holding them down, and the Trieste began to ascend. The ascent was much faster than the descent, taking only 3 hours and 15 minutes. When they surfaced, they had become the first humans ever to reach the deepest point on Earth. For over 50 years after Walsh and Piccard's dive, no one returned to Challenger Deep. Unmanned vehicles went down, remote-operated vehicles and autonomous probes, but no human set eyes on the bottom again until 2012. In that year, filmmaker James Cameron, famous for directing movies like Titanic and Avatar, but also a passionate ocean explorer, made a solo descent in a submersible he helped design called the Deep Sea Challenger. Cameron's submersible was more advanced than the Trieste. It was smaller, more maneuverable, equipped with high-definition cameras and mechanical arms for collecting samples. The viewing port was much larger and much thicker, about 9.5 inches of specially designed acrylic capable of withstanding the enormous pressure. On March 26, 2012, Cameron made the descent, reaching a depth of 10,908 meters. He spent several hours on the bottom, filming, collecting samples, exploring the terrain in ways Walsh and Piccard never could. Cameron's footage revealed a landscape similar to what the Trieste had seen, flat, covered in fine sediment, eerily empty-looking at first glance. But he also captured images of small amphipods, shrimp-like crustaceans scurrying across the bottom, and other signs of life. His samples included rocks, sediment, and even some small organisms that would later be studied in labs. The dive was part of the Deep Sea Challenge expedition, a partnership with National Geographic, and it brought images of Challenger Deep to a global audience for the first time. Cameron's dive was remarkable, but he went alone, and he went once. The next major series of dives would push the limits even further. In 2019, American explorer and private equity investor Victor Vescovo launched the 5 Deeps expedition, an ambitious project to reach the deepest point in each of the world's 5 oceans. For the Pacific, that meant Challenger Deep. Vescovo descended multiple times in April and May of 2019 in a submersible called the Limiting Factor, a 2-person titanium-hulled vessel built to withstand full ocean depth. On April 28, he reached a depth of 10,928 meters, the deepest any human has ever gone, 16 meters deeper than Walsh and Piccard's Trieste. He made 4 dives to Challenger Deep during that expedition, becoming the first person to visit the bottom more than once. He even brought passengers on later dives, including Patrick LaHaye, the co-designer of the limiting factor. Vescovo's dives were longer and more thorough than previous visits. He spent hours at the bottom, traversing the terrain, filming, collecting samples of rocks and biological specimens, and disturbingly, he found evidence of human impact even at the deepest point on Earth: plastic. He observed a plastic bag and candy wrappers lying on the sediment, proof that pollution has reached even this most remote location. It was a sobering discovery, a reminder that no place on Earth is truly beyond the reach of human activity. Between 2019 and 2020, Vescovo returned to Challenger Deep several more times as part of the Ring of Fire expedition, making a total of multiple dives and bringing other researchers and explorers with him. These repeated visits have provided more data about the trench than all previous expeditions combined. For the first time, scientists have been able to study Challenger Deep not as a one-time destination, but as a place that can be visited repeatedly, studied over time, compared between visits. In 2020, China sent a manned submersible called Fendouche, meaning striver, to the Mariana Trench. Between October and November, it completed 13 dives, reaching depths over 10,900 meters and collecting biological and geological samples. The Chinese team reported discovering thousands of worms and mollusks, the deepest colony of such organisms ever observed, found at depths ranging from 8,200 feet to 31,000 feet. These human visits to Challenger Deep, still fewer than 20 crewed descents in total, represent the cutting edge of ocean exploration. Each dive is an engineering marvel, requiring technology pushed to its absolute limits. The pressure at depth is so enormous that even tiny flaws in design can be catastrophic. The darkness is so complete that powerful lights are essential, and the cold is so intense that systems must be carefully insulated. And yet we've done it. We've sent people to the bottom of the world and brought them back safely. As you rest tonight, think about those explorers, Walsh and Picard, crammed into a tiny steel sphere, descending for 5 hours through the darkness, not knowing if their vessel would hold. Cameron, alone in his submersible, surrounded by cameras and instruments, filming the abyss. Vescovo, making dive after dive, driven by curiosity and the desire to understand. These are explorers in the truest sense, venturing into an environment as alien as any in our solar system, risking their lives to see what no one else has seen, to bring back knowledge from the deep. The technology that made these dives possible has evolved dramatically over the decades, from weighted ropes to echo sounders, to manned submersibles to remotely operated vehicles. Our tools for exploring the deep ocean have become more sophisticated and capable. And yet, the deep ocean remains largely unexplored. We've mapped less than 20% of the ocean floor in high resolution. Most of the deep sea has never been seen by human eyes, or even by cameras. The Mariana Trench, despite being the most famous deep-sea feature on Earth, is still mostly unknown. We've visited a few spots, taken some samples, but vast areas remain untouched, unexplored, waiting for future generations to discover their secrets. Life in the crushing deep. When the Trieste first reached the bottom of Challenger Deep in 1960, the crew reported seeing what they thought was a flatfish. Many scientists doubted this claim, thinking nothing could survive the enormous pressure at such depths. But subsequent visits and samples have confirmed something remarkable. Life not only exists in the Mariana Trench, it thrives there. The trench is not a sterile, lifeless wasteland. It's an ecosystem, strange and extreme, but full of organisms that have adapted to conditions we can barely imagine. One of the most successful creatures in the deep ocean is the snailfish. These gelatinous fish have been found at depths exceeding 8,000 meters, making them the deepest living fish known to science. In 2014, a new species of snailfish was discovered at a depth of 8,145 meters in the Mariana Trench, breaking the previous record. Then in 2017, an unidentified snailfish was filmed at 8,178 meters. Snailfish are remarkable creatures, perfectly adapted for hadal depths. They don't have swim bladders, the gas-filled organs that help most fish control their buoyancy. At such extreme pressures, a swim bladder would collapse and become useless. Instead, snailfish have soft, gelatinous bodies that compress slightly under pressure but don't rupture. They lack scales, and their skin is translucent, sometimes almost transparent. When brought to the surface, where pressure is much lower, they often appear bloated and deformed, but at depth, they're sleek and elegant, gliding over the bottom in search of small crustaceans to eat. The snailfish's body contains high concentrations of a compound called trimethylamine N oxide, or TMAO. This organic molecule helps stabilize proteins and cell membranes under high pressure. It prevents the proteins from being crushed and distorted by the enormous forces pressing in from all sides. The deeper a fish lives, the more TMAO it needs. At the depths where snailfish live, their tissues are saturated with it. It's one of the key adaptations that allows them to survive where almost nothing else can. Another common resident of the Mariana Trench is the amphipod, a small crustacean somewhat resembling a shrimp. Amphipods are found throughout the ocean, but in the Hadal zone, they exhibit a phenomenon called deep-sea gigantism. While most amphipods are small, perhaps a few centimeters long, some species in the Mariana Trench grow much larger. Supergiant amphipods can reach lengths of over 30 centimeters, roughly the size of a dinner plate. They're scavengers, feeding on whatever organic matter drifts down from above or on the occasional carcass of a larger animal that sinks to the bottom. These supergiant amphipods have special adaptations to handle the pressure. Their exoskeletons contain aluminum, making them the first known species to use this metal for structural purposes. They ingest aluminum through sediments on the seafloor and incorporate it into their shells in a form that provides extra strength. It's an ingenious solution to the problem of maintaining body structure under crushing pressure. Amphipods play a crucial role in the trench ecosystem. They're the cleanup crew, consuming dead organic matter and breaking it down into forms that other organisms can use. Without scavengers like amphipods, the ecosystem would be choked with debris, but their presence has also revealed something troubling. In a 2019 study, scientists examined amphipods collected from the Mariana Trench and found that 100% of them had ingested plastic. Every single individual contained microplastics in its gut. The plastic had broken down into tiny particles and drifted down through the water column, and the amphipods, feeding on whatever organic matter they could find, had consumed it along with their food. Sea cucumbers are another common sight on the floor of the Mariana Trench. These echinoderms related to starfish and sea urchins are slow-moving deposit feeders. They crawl along the bottom, scooping up sediment with specialized tube feet around their mouths, digesting the organic material within it, and expelling the rest. Some species never touch the bottom at all, floating in the water column for their entire lives, drifting with the currents. Sea cucumbers have gelatinous bodies that compress under pressure, and they play an important role in recycling nutrients. They're among the most abundant large animals on the deep sea floor, and in some areas of the trench, they outnumber all other visible life forms. Then there are the xenophyophores, some of the strangest creatures in the deep ocean. These are single-celled organisms, but unlike most single-celled life, they're enormous. Some xenophyophores can grow to 10 centimeters or more across, the size of a grapefruit, making them among the largest single-celled organisms on Earth. They create intricate shells from particles they gather from the water, sediment grains and bits of organic matter, all glued together into delicate structures. These shells can take many forms, sometimes branching like trees, sometimes sprawling across the sediment in complex patterns. Xenophyophores are extremely fragile. Their shells are so delicate that bringing them to the surface intact is nearly impossible. Even slight disturbances can cause them to crumble. Scientists have had to develop special sampling techniques just to study them. Despite their fragility, they're remarkably successful in the Hadal environment, found at depths over 10,000 meters. How they manage to maintain such large, delicate structures under such enormous pressure is still not fully understood. But they clearly have adaptations that allow them to thrive where few other organisms can. Acorn worms, gelatinous creatures that resemble smooth earthworms, live in the sediment of the trench. They have a proboscis, a collar, and a long cylindrical trunk forming the main part of their body. They feed by ingesting sediment and extracting organic matter from it, much like earthworms do on land. They breathe through gill-like structures, similar to fish. Acorn worms in the family Torquatoridae have been found living in the Mariana Trench, their gelatinous bodies well suited to the extreme pressure. Jellyfish have also been discovered in the trench, drifting through the dark water. One species found in 2016 has a clear body with red stripes and luminous yellow orbs inside. It possesses two sets of tentacles, one short and one long, for catching prey. This jellyfish, placed in the genus Crossota, is widespread throughout the world's oceans, but its presence in the Mariana Trench shows that even creatures we think of as delicate and fragile can adapt to hadal conditions. One of the most unusual findings in recent expeditions has been the discovery of bacterial mats and microbial communities in areas where serpentinization is occurring. Serpentinization is a geological process where water reacts with certain types of rock from the Earth's mantle, producing hydrogen and methane. These gases can serve as energy sources for specialized bacteria, which form the base of a food web independent of sunlight. Some scientists believe that serpentinization environments might have been where life on Earth first began, billions of years ago, because they provide chemical energy without needing photosynthesis. All of these creatures, from snailfish to amphipods to single-celled giants, share certain adaptations. They lack air-filled cavities that would collapse under pressure. They have flexible, often gelatinous bodies. Their proteins contain special compounds like TMAO that prevent crushing. Many are transparent or nearly so, perhaps because coloration is unnecessary in total darkness. Many lack eyes or have very small, reduced eyes, since there's nothing to see. Instead, they rely on other senses: touch, chemical detection, vibration sensitivity. The food chain in the Mariana Trench is entirely dependent on what falls from above. There's no photosynthesis at such depths, no plants or algae producing energy from sunlight. Instead, the ecosystem relies on marine snow, a continuous gentle rain of organic material falling from the sunlit zones above. Dead plankton, fecal pellets, fragments of larger animals all slowly sink through the water column. By the time this material reaches hadal depths, most of its nutritious content has been consumed by organisms higher up. What arrives is largely poor quality detritus. But bacteria specialize in breaking down this poor quality material and converting it into forms that other organisms can use. The bacteria multiply, forming mats on the sediment or clumps in the water, and they become food for deposit feeders like sea cucumbers and amphipods. Those scavengers, in turn, become food for predators like snailfish. It's a food web built on scraps, on leftovers, but it works. The ecosystem is less productive than surface waters, certainly, but it's functional, sustaining a surprising diversity of life. Occasionally, something larger sinks to the bottom. A whale carcass, a large fish, a mass of kelp torn loose by a storm. When this happens, it's like a feast. Scavengers from miles around are drawn to the site, attracted by chemical cues in the water. They converge on the bonanza, feeding until nothing remains but bones and fragments. These rare events provide bursts of energy to the ecosystem, sustaining it through long periods when only the slow rain of marine snow provides nutrition. The fact that life exists in the Mariana Trench at all is remarkable. The fact that it's diverse, that there are multiple species filling different ecological roles, is astonishing. These are not primitive organisms barely clinging to survival. They're specialized, successful species well adapted to their environment. They've been evolving for millions of years in the trenches, developing unique solutions to the challenges of pressure, cold, and darkness. In some ways, they're more sophisticated than their shallow water relatives, because the conditions they face are so much more extreme. As you rest, think about these creatures living their entire lives in absolute darkness under crushing pressure. They know nothing of sunlight, nothing of warmth, nothing of the surface world. To them, the hadal zone is normal, home, the only environment they've ever known. They don't struggle against the pressure. Their bodies are built for it. They don't miss the light. They've never experienced it. They're as perfectly suited to challenge a deep as we are to the surface, and in their own strange way, they're thriving in one of the most extreme environments on Earth. Strange chemistry and hidden vents. The Mariana Trench is not just a place of extreme physical conditions. It's also a place of unusual chemistry, where processes happening deep within the Earth create environments that blur the line between geology and biology. Scattered throughout the trench and its surrounding regions are hydrothermal vents and mud volcanoes, places where heat and minerals from below interact with cold seawater to create unique habitats. Hydrothermal vents are openings in the seafloor where heated water emerges. They form in areas of volcanic activity, places where magma from the mantle rises close to the surface. Cold seawater seeps down through cracks in the seafloor, gets heated by the magma below, dissolves minerals from the rock, and then rises back up, emerging from the vent as superheated, mineral-rich fluid. The water coming out of some vents can reach temperatures exceeding 700 degrees Fahrenheit, hot enough to melt lead, though the intense pressure prevents it from boiling. Around the Mariana Trench, hydrothermal vents are found primarily in two areas, the volcanic arc and the back arc. The volcanic arc is a chain of submarine volcanoes paralleling the trench, about 200 kilometers to the west. These volcanoes form as magma, generated by the subducting Pacific Plate, rises through the Mariana Plate and erupts. Many of these volcanoes are active, and about a third of them are known to have hydrothermal vents on their slopes. The back arc is even farther from the trench, a zone where the overriding plate is being pulled apart by extensional forces, creating new seafloor. This spreading is similar to what happens at mid-ocean ridges, and like mid-ocean ridges, the back arc has volcanic activity and hydrothermal vents. The Mariana Trough, the back arc basin behind the Mariana Islands, contains numerous vent sites, though it's been less extensively explored than other regions. These vents are not all the same. They vary in temperature, in the minerals they release, and in the communities of life they support. Some vents release water black with dissolved metals, forming structures called black smokers. As the hot, metal-rich water hits the cold seawater, the dissolved metals precipitate out, forming chimney-like structures of sulfide minerals. Some of these chimneys can grow to tens of meters tall, towers of rock built from mineral precipitation, constantly growing as long as the vent remains active. Other vents release clear, shimmering water, slightly warmer than the surrounding seawater, but not superheated. These diffuse flow vents support different communities of organisms, and some vents are truly bizarre. At the northwest Efuku volcano in the Mariana region, there are vents that release bubbles of liquid carbon dioxide. The pressure at depth is high enough that carbon dioxide becomes liquid, and these vents spew it out like a carbonated spring, earning them the nickname champagne vents. There are even vents that erupt molten sulfur, yellow streams of liquid sulfur flowing across the seafloor like lava. But some of the strangest features in the Mariana region are not vents at all, they're mud volcanoes. These seamounts, rising from the seafloor, erupt not lava but serpentinite mud, a slurry of altered rock, water, and dissolved gases. They form in the Foreg region, the zone between the trench and the volcanic arc, and they're directly connected to the subduction process happening below. As the Pacific Plate descends, it carries with it sediments and hydrated basalt, rock, that contains water trapped in its mineral structure. As the plate is pushed deeper and deeper, the increasing temperature and pressure force this water out. The water rises upward into the mantle wedge above the subducting plate, where it reacts with peridotite, a type of rock from the Earth's mantle. This reaction is called serpentinization, and it transforms the peridotite into serpentinite, a softer, more slippery rock. The serpentinite, mixed with water and gases, becomes buoyant and rises through cracks and faults in the overlying plate, eventually erupting at the surface as a mud volcano. There are at least 10 known serpentinite mud volcanoes in the Mariana Foreg, and they're all actively erupting. Some of them, like South Chamorro, Conecuh Seamount, and Asu Tesoro, have been studied extensively. The mud they erupt contains pieces of mantle rock, sometimes barely altered, along with fragments of subducted seamounts, even pieces of coral that were once growing in shallow tropical waters and have now been carried kilometers deep and regurgitated at the surface. The fluids coming out of these mud volcanoes are unusual. They're highly alkaline, with pH values sometimes exceeding 12, far more basic than seawater. They're rich in hydrogen and methane, gases produced by the serpentinization reaction. These gases are energy sources, and they support entire ecosystems based not on photosynthesis but on chemosynthesis. Chemosynthesis is the process by which certain bacteria convert chemical energy into biological energy. Instead of using sunlight like plants, these bacteria use chemicals like hydrogen sulfide, methane, or hydrogen. They take these inorganic compounds and use the energy released by reacting them with other chemicals to build organic molecules. These bacteria form the base of the food web at hydrothermal vents and serpentinite mud volcanoes, supporting animals that feed on them or that host them as symbionts. One of the most remarkable discoveries in the Mariana region was the Shinkai Seep Field, found in 2010 during a dive by the Japanese submersible Shinkai 6500. This site, located in the southern Mariana Fork, features abundant vesicomide clams living in association with a serpentinite-hosted system. Vesicomide clams are common at hydrothermal vents and cold seeps elsewhere in the ocean, but finding them at a serpentinite site in a subduction zone was unexpected. These clams don't eat in the conventional sense. They have tiny mouths and reduced digestive systems. Instead, they host symbiotic bacteria in their gills. The bacteria perform chemosynthesis, using hydrogen sulfide or methane from the vent fluids to produce organic compounds, and the clam absorbs these compounds as nutrition. It's a partnership. The clam provides the bacteria with a safe place to live and access to chemicals, and the bacteria provide the clam with food. The clam essentially farms bacteria inside its own body. The Shinkai Seep Field is unusual because there's no obvious heat source nearby. Unlike vents on volcanic arcs or mid-ocean ridges, where magma provides heat, the serpentinization at this site seems to be driven entirely by the persistent flow of fluids from the subducting slab below. It's a cold seep, not a hot vent, yet it supports a thriving community of life. The site has tall carbonate chimneys, some reaching several meters high, formed by the precipitation of minerals from the alkaline fluids. Serpentinization environments like this are of particular interest to astrobiologists, scientists who study the potential for life beyond Earth. The reason is simple. Serpentinization can occur without sunlight, without photosynthesis, and potentially without a dense atmosphere. It's driven by water reacting with certain types of rock, producing hydrogen and methane, which can support life. Similar processes might be happening on other worlds. Europa, one of Jupiter's moons, is covered in ice, but beneath that ice is a global ocean of liquid water. The bottom of Europa's ocean might have serpentinization reactions occurring where water contacts the moon's rocky mantle. If so, Europa could have hydrothermal vents, chemical energy sources, and possibly life, all without any sunlight reaching the surface. The same might be true of Enceladus, a moon of Saturn that also has a subsurface ocean. Studying serpentinization in the Mariana Trench helps us understand what might be possible elsewhere in our solar system. Some scientists have even suggested that serpentinization environments might have been where life on Earth first began. Billions of years ago, before photosynthesis evolved, before oxygen filled the atmosphere, life would have needed another energy source. Chemical reactions like those occurring at serpentinite mud volcanoes or hydrothermal vents could have provided that energy. The first organisms might have been chemosynthetic bacteria, living off hydrogen and methane in an environment very much like the Shinkai Seep Field. The chemistry of the Mariana Trench is not uniform. It varies from place to place, depending on the local geology, the activity of vents or mud volcanoes, and the flow of currents. In some areas, the water is rich in dissolved oxygen, brought down from the surface by circulation. In other areas, especially near vents, oxygen is depleted, and the water is rich in sulfides, methane, and other reduced compounds. This chemical heterogeneity creates a variety of habitats, each with its own suite of adapted organisms. As you rest tonight, imagine these hidden oases in the trench, vents spewing superheated water, black with dissolved metals, surrounded by clusters of strange tube worms and crabs. Mud volcanoes quietly erupting serpentinite slurry, their flanks covered in clams farming bacteria in their gills. Champagne vents releasing streams of carbon dioxide bubbles, shimmering as they rise through the water. These are environments unlike anything on the surface, driven by processes deep within the planet, supporting life in ways that don't depend on the sun. They're reminders that life is tenacious, adaptable, capable of finding a foothold in places we never expected, as long as there's energy to be harvested and water to sustain it. What drifts down from above? In the perpetual darkness of the Mariana Trench, thousands of meters below the sunlit surface, there is no photosynthesis, no algae, no seaweed, no plants of any kind can grow where light never reaches, and yet the ecosystem survives. It survives because of a slow, constant rain of organic material falling from the zones above, a gentle, invisible snowfall that provides the foundation for all life at Hadal depths. Scientists call it marine snow, and without it, the deep ocean would be a sterile wasteland. Marine snow consists of tiny particles drifting downward through the water column, dead phytoplankton, the microscopic algae that bloom in sunlit surface waters, fecal pellets from zooplankton and fish, sticky clumps of waste that sink faster than individual particles, molted shells and exoskeletons shed by crustaceans, bits of dead fish, fragments of jellyfish, pieces of algae broken off by waves or currents. All of this organic matter, produced in the sunlit layers of the ocean, eventually dies or is expelled, and gravity pulls it downward. The journey from surface to trench bottom can take weeks, even months. As the particles sink, they're constantly being consumed. Bacteria coat every surface, breaking down complex organic molecules into simpler forms. Small zooplankton intercept sinking particles, feeding on them and repackaging them into their own fecal pellets, which sink faster. Fish and squid in the mesopelagic zone, the twilight zone, feed voraciously on the sinking material, consuming the most nutritious parts. By the time marine snow reaches the Hadal zone, most of its energy has been extracted. What arrives at the bottom is largely detritus, the leftover scraps that nothing higher up wanted. And yet, it's enough. Bacteria in the trench specialize in breaking down even these poor quality materials, extracting the last bits of usable energy. These bacteria multiply, forming films on the sediment surface, and they become food for deposit feeders. Sea cucumbers crawl across the bottom, scooping up sediment and digesting the bacteria within it. Amphipods sift through the ooze, searching for organic particles. Worms burrow through the mud, consuming bacteria and detritus as they go. The entire ecosystem is built on this slow rain of marine snow, a trickle of energy from the sunlit surface, sustaining life in the absolute darkness of the abyss. But occasionally, something much larger sinks to the bottom. A whale dies in the open ocean, and its massive carcass, weighing tons, begins the long descent. It might take days to reach the trench floor, but when it does, it's a bonanza, a sudden influx of energy into an ecosystem that's usually starved for nutrition. The smell, or more accurately, the chemical signals released by decomposition, spread through the water. Amphipods from kilometers away detect the signals and begin to move toward the source. Within hours, the carcass is covered with scavengers. Amphipods swarm over it, tearing off chunks of flesh and blubber. Hagfish, eel-like creatures that usually burrow into sediment, emerge and burrow into the whale, eating from the inside out. Sleeper sharks, rare visitors to Hadal depths, might arrive to feed on the softer tissues. Over weeks and months, the carcass is reduced to bones and a scatter of fragments. Even the bones are eventually consumed by specialized worms that bore into them, digesting the lipids stored within. A whale fall can support a localized ecosystem for years, even decades. First come the scavengers that eat the flesh, then come organisms that consume the fats soaking into the sediment around the carcass. Eventually, the bones themselves become habitat for specialized bacteria that break down the remaining organic compounds. These bacteria, in turn, support animals like worms and clams. A single whale fall in the deep ocean can sustain hundreds of species, providing a rare pulse of energy that ripples through the food web. But not everything that sinks to the trench is natural. In recent decades, human-made materials have begun to accumulate in the deepest parts of the ocean. Plastic, the ubiquitous material of modern life, has found its way to Challenger Deep. Victor Vescovo, during his 2019 dives, observed a plastic bag and candy wrappers lying on the sediment at nearly 11,000 meters depth. Plastic bottles, fishing gear, packaging materials, all of it drifts down just like marine snow, carried by currents and gravity into the abyss. Plastic doesn't biodegrade the way organic matter does. It breaks down into smaller and smaller pieces, forming microplastics and eventually nanoplastics, but it doesn't truly disappear. These tiny plastic particles are now ubiquitous in the ocean, found at every depth, in every region. And organisms are consuming them. The amphipods in the Mariana Trench, those supergiant scavengers that clean up organic material, are also ingesting plastic. Studies have shown that 100% of amphipods collected from Hadal depths contain microplastics in their guts. The plastic enters the food web. Amphipods eat it, thinking it's food. Fish eat the amphipods, ingesting the plastic along with them. The plastic can't be digested, can't be broken down, so it accumulates, passing up the food chain. What effects this has on the animals is still being studied, but it's unlikely to be beneficial. Plastic can block digestive tracts, leach toxic chemicals, and fill stomachs with indigestible material that provides no nutrition. The presence of plastic in the Mariana Trench is a stark reminder that human impacts are global. We tend to think of the deep ocean as remote, untouched, far from human influence. But there is nowhere on Earth that remains truly pristine. The plastic we throw away, the chemicals we release, the changes we make to the atmosphere and ocean, they all have effects that reach even the deepest, most inaccessible places. Pollution isn't the only human impact reaching the trench. Chemical contaminants have also been found at hadal depths, polychlorinated biphenyls or PCBs, toxic compounds used in electrical equipment and banned in the 1970s, have been detected in high concentrations in amphipods and other organisms from the Mariana Trench. These chemicals were released into the environment decades ago, mostly through industrial accidents and improper disposal. They don't break down easily, and they've spread throughout the ocean, accumulating in the fatty tissues of animals. Somehow they've made their way to the bottom of the world, concentrating in organisms that live there. The levels of PCBs in some trench amphipods are comparable to levels found in some of the most polluted coastal areas on Earth, places like Suruga Bay in Japan, which is near industrial centers. How contaminants from human industry ended up in the same concentrations in the most remote part of the ocean as in a heavily polluted bay is a question scientists are still working to answer. It likely involves complex pathways, PCBs attached to sinking particles, transport by ocean currents, bioaccumulation as contaminants pass up the food chain. Climate change, too, is affecting the deep ocean, though the mechanisms are complex. As the surface ocean warms, it holds less dissolved oxygen. Oxygen concentrations in deep water are declining, a phenomenon called ocean deoxygenation, while the trench itself still has relatively high oxygen levels, brought down by deep currents from polar regions. The overall trend is concerning. If oxygen levels continue to drop, it could affect the organisms living at hadal depths, especially those with high metabolic rates. The Mariana Trench, for all its remoteness, is not isolated from the surface world. It's connected by the slow rain of marine snow, by the circulation of ocean currents, by the sinking of contaminants and debris. What happens at the surface eventually affects the deep. And as human activity continues to alter the planet, those effects will reach even the most extreme environments. The trench is a reminder that Earth's systems are interconnected, that there are no true frontiers, no places so remote that they remain untouched. As you rest, think about that connection. The surface and the abyss, linked by falling particles, by currents, by the slow exchange of water and nutrients. What we do on land, what we release into rivers and oceans, eventually finds its way down through the zones, down to the very bottom. The Mariana Trench is not separate from the world we inhabit. It's part of the same ocean, the same planet, subject to the same forces, and increasingly to the same human influences. And what we discover there, what we learn about the effects of our actions, might help us understand how to live more gently on this world we share with countless other forms of life. The invisible residents. When we think of life in the Mariana Trench, we tend to imagine the creatures we can see: fish, amphipods, sea cucumbers. But the most abundant life by far, the life that truly dominates the hadal ecosystem, is invisible to the naked eye. Bacteria and archaea, single-celled microorganisms, exist in numbers that dwarf all the larger animals combined. They coat every surface, float in the water column, burrow through the sediment, and form the foundation of the entire food web. Without them, the trench would be lifeless. Microbes are astonishingly diverse in the deep ocean. There are thousands, probably millions of species, each adapted to slightly different conditions, each playing a specific role in the ecosystem. Some are decomposers, breaking down the organic material in marine snow and releasing nutrients that other organisms can use. Others are chemosynthetic, harvesting energy from chemical reactions instead of from sunlight. Still others are predators, hunting and consuming other microbes. And some are symbionts, living inside or on the bodies of larger organisms in mutually beneficial relationships. At the bottom of Challenger Deep, researchers have found monothalamia, single-celled organisms that belong to a group called foraminifera. These creatures have been found at record depths of over 10,600 meters. Monothalamia are larger than most single-celled organisms. visible to the naked eye if you know what to look for. But they're still microscopic in the sense that they consist of just one cell. They create shells from organic material or sediment particles, and they move slowly across the sediment surface, feeding on bacteria and organic detritus. The fact that such simple, single-celled organisms can survive at the very deepest point on Earth is remarkable. It suggests that the fundamental requirements for life, liquid water, energy, and the right chemistry, are met even in the most extreme environment. And if life can exist in Challenger Deep, it raises the possibility that life might exist in other extreme environments in our solar system, places we once thought too harsh for biology. Bacteria in the trench have adapted to the extreme pressure in ways scientists are still trying to understand. Pressure affects the structure of proteins and cell membranes. Under normal pressure, proteins fold into specific shapes that allow them to function. Under extreme pressure, those shapes can distort, causing the proteins to lose their function. But deep-sea bacteria have evolved proteins that remain stable even when crushed by 1,000 atmospheres of pressure. Some of these adaptations involve the use of special molecules like TMAO, which we've already encountered in snailfish. Others involve changes to the amino acid sequences of the proteins themselves, altering their structure in ways that make them pressure-resistant. Cell membranes, the thin barriers that surround all cells, also have to adapt. Under high pressure, normal cell membranes become too rigid, losing their flexibility and function. Deep-sea bacteria adjust the composition of their membranes, incorporating more unsaturated fatty acids, which remain fluid even under pressure. It's a subtle change, but it makes the difference between life and death at Hadal depths. Microbes in the trench also have to deal with the cold. At temperatures just above freezing, chemical reactions slow down. Enzymes, the proteins that catalyze reactions in living cells, work less efficiently. But cold-adapted bacteria have enzymes that function well at low temperatures, allowing them to maintain their metabolism even in the near-freezing water of the abyss. Some of the most interesting microbes in the trench are the chemolithotrophs, organisms that obtain energy by oxidizing inorganic compounds. At hydrothermal vents and serpentinite mud volcanoes, these bacteria thrive. They use hydrogen, methane, or hydrogen sulfide as energy sources, converting these chemicals into forms that cells can use. The energy released by these reactions is then used to fix carbon dioxide, turning it into organic molecules. These bacteria are primary producers, the equivalent of plants in a sunlit ecosystem, and they support entire food webs without any need for sunlight. One particularly fascinating group of microbes found in the trench are the methanogens, archaea, that produce methane as a byproduct of their metabolism. Methanogens are anaerobes, meaning they don't need oxygen. In fact, oxygen is toxic to many of them. They live in the sediment, in oxygen-poor pockets, and they play a key role in the carbon cycle. By producing methane, they convert organic carbon into a gas that can eventually make its way back to the atmosphere. Some of the methane produced by methanogens in the deep ocean rises through the water column and is released at the surface, contributing to atmospheric methane levels and thus to the global climate. Another group of archaea, the ammonia-oxidizing archaea, are abundant in deep-sea sediments. They obtain energy by converting ammonia, produced by the decomposition of organic matter, into nitrite. This is a crucial step in the nitrogen cycle, transforming nitrogen from one form into another, making it available for other organisms to use. Without these archaea, nitrogen would accumulate in forms that most organisms can't utilize, and the entire ecosystem would grind to a halt. Microbes in the Mariana Trench have been found to possess genes and metabolic pathways that are unique, not seen in their relatives in shallower waters. These unique adaptations are the result of millions of years of evolution in isolation, under conditions that favor certain traits over others. Studying these microbes can reveal fundamental principles about how life adapts to extreme environments, and it can also lead to practical applications. Enzymes from deep-sea bacteria, for example, are often stable under conditions that would destroy normal enzymes. These so-called extremozymes have potential uses in industry, biotechnology, and medicine. Scientists are particularly interested in the possibility that microbes in the trench might produce novel compounds, chemicals not found anywhere else. Deep-sea bacteria, living in such an unusual environment might have evolved novel metabolic pathways that produce unique molecules. Some of these molecules could have antibiotic properties, anti-cancer activity, or other biomedical uses. Exploring the microbial diversity of the Mariana Trench is, in a sense, exploring a vast chemical library, one that nature has been curating for millions of years. The microbial communities in the trench are not randomly distributed. They're structured, organized into communities based on local conditions. Near hydrothermal vents, the community is dominated by chemolithotrophs, organisms that harvest energy from vent chemicals. In sediments far from vents, the community is dominated by heterotrophs, organisms that consume organic matter. Different depths, different temperatures, different oxygen levels, all select for different microbial species. One of the most important functions microbes perform in the trench is nutrient cycling. They break down organic matter, releasing nitrogen, phosphorus, and other nutrients back into the water, where they can be used by other organisms. They fix carbon dioxide, converting it into organic molecules. They produce gases like methane and hydrogen sulfide. They mediate the chemistry of the entire ecosystem, acting as invisible engineers that maintain the conditions necessary for life. And they're incredibly abundant. In a single gram of sediment from the Mariana Trench, there can be millions, even billions of microbial cells. Multiply that by the vast area of the trench floor, and you're talking about astronomical numbers. A microbial biomass that far exceeds the biomass of all the visible animals combined. The trench is, first and foremost, a microbial habitat. The larger animals, impressive as they are just a small part of the story. As you drift towards sleep, think about these invisible residents, bacteria and archaea, each one a microscopic marvel, adapted to survive where almost nothing else can. They don't just survive, they thrive, processing chemicals, cycling nutrients, forming the foundation of an entire ecosystem. They're the true masters of the Mariana Trench, and without them, the whole system would collapse. In their tiny invisible lives, they carry out processes that are essential not just for the trench, but for the entire ocean, and ultimately for the planet. They're a reminder that life's complexity and importance aren't always visible to the eye, that sometimes the smallest organisms play the largest roles. Exploration and discovery. The Mariana Trench has been explored, but only barely. Despite being the most famous deep-sea feature on Earth, despite decades of interest and research, vast areas of it remain completely unknown. We visited a handful of sites, collected samples from a few locations, mapped some of the terrain, but the trench is over 1,500 miles long, and we've seen only a tiny fraction of it. It's one of the least explored places on Earth, and every new expedition reveals surprises. Modern exploration of the trench relies on a combination of technologies. There are manned submersibles, like the limiting factor, capable of carrying people to full ocean depth. These submersibles are expensive, complex, and risky to operate, but they allow scientists to see the trench with their own eyes, to make observations that cameras and sensors might miss. There are remotely operated vehicles, or ROVs, tethered to ships at the surface, controlled by pilots who watch video feeds and manipulate robotic arms to collect samples. ROVs can stay down much longer than manned submersibles and can go places too dangerous for humans. There are autonomous underwater vehicles, or AUVs, which are untethered robots that follow pre-programmed missions. AUVs can map the seafloor, measure water properties, and collect data over large areas without direct human control. They're particularly useful for creating high-resolution bathymetric maps, detailed pictures of the seafloor's topography. And there are landers, free-falling platforms loaded with instruments and bait, dropped from ships to sink to the bottom. Landers sit on the seafloor for hours or days, recording video, collecting samples, and then drop their ballast and float back to the surface. Each technology has strengths and limitations, and a comprehensive exploration program uses all of them. The combination of manned dives, ROV surveys, AUV mapping, and lander deployments gives scientists the best possible picture of what the trench is like. But even with all these tools, progress is slow. The trench is deep, far from shore, difficult to reach. Expeditions are expensive and require specialized ships and equipment. Funding is limited, and there are always more questions than resources to answer them. One of the biggest challenges in trench exploration is simply finding things. The ocean is vast, The trench is narrow, and specific features like hydrothermal vents or unusual geological formations can be small and widely scattered. Scientists use a combination of clues to locate interesting sites. They look for chemical signals in the water, plumes of warm or mineral-rich water that indicate a vent nearby. They use sonar to map the seafloor, looking for unusual topography like seamounts or fissures that might host vents. They deploy landers with bait to attract scavengers, then return later to see what's been drawn to the site. Recent expeditions have made remarkable discoveries. In 2014, scientists aboard the research vessel Falkor, operated by the Schmidt Ocean Institute, deployed landers at various depths in the Mariana Trench and discovered new species of snailfish, including the deepest fish ever recorded. They also found supergiant amphipods, collected rock samples from the inner slope of the trench, and mapped large areas of the seafloor in high resolution. The expedition broke multiple records and provided crucial data about the ecology and geology of the trench. In 2015, another expedition focused on understanding the microbial life and the food web in the trench. Scientists used landers equipped with cameras and bait to observe scavengers and collected sediment cores to study the microbial communities. They found that life in the trench is more abundant and diverse than previously thought, and that food webs are complex, with multiple trophic levels and intricate interactions between species. In 2016, NOAA's research vessel Okeanos Explorer conducted an expedition to the Mariana region, using ROVs to explore hydrothermal vents and mud volcanoes. The team discovered new vent fields, observed unique biological communities, and collected samples of vent fluids and minerals. They found vents releasing liquid carbon dioxide and molten sulfur, environments unlike anything seen elsewhere on Earth. The Five Deeps expedition, led by Victor Vescovo in 2019, was a landmark in trench exploration. Over the course of a year, Vescovo and his team visited the deepest point in each of the world's 5 oceans, including Challenger Deep in the Mariana Trench. They collected the first ever rock samples from the deepest point on Earth, found new species, and documented the presence of plastic pollution at extreme depths. The expedition's data is still being analyzed, and it's likely to yield insights for years to come. China's Fendouge submersible, deployed in 2020, conducted multiple dives in the trench, reaching depths over 10,900 meters. The Chinese team collected biological and geological samples, filmed deep-sea creatures, and tested new technologies for hadal exploration. Their work has added to the growing body of knowledge about the trench and demonstrated that hadal science is now a global effort, with multiple countries contributing. One of the most important outcomes of recent expeditions has been the creation of high-resolution maps of the trench. Using multi-beam sonar systems, scientists have mapped large sections of the Mariana Trench floor in detail, revealing features that were previously unknown. These maps show seamounts, fissures, landslides, and other structures that provide clues about the trench's geological history. They also help scientists plan future dives, identifying sites that are likely to be scientifically interesting. Mapping efforts like Seabed 2030, an international project aiming to map the entire ocean floor by the year 2030, will eventually include detailed surveys of the Mariana Trench. This project, if successful, will provide a complete picture of the ocean's topography, revealing features and structures that we don't yet know exist. For the Mariana Trench, this means that future explorers will have much better maps to work with, allowing them to target specific sites for closer study. But maps can only tell us so much. To truly understand the trench, we need to go there, to observe, to collect samples, to document the life and geology firsthand. And that's where the future of trench exploration lies. New technologies are being developed all the time. Submersibles are becoming more capable, able to dive deeper, stay down longer, and carry more instruments. ROVs are becoming more sophisticated, with better manipulators, higher resolution cameras, and more sensors. AUVs are becoming smarter, able to navigate autonomously in complex terrain and adapt to unexpected conditions. One promising development is the use of hybrid vehicles that combine the strengths of ROVs and AUVs. These vehicles can operate tethered when precision is needed, then detach and operate autonomously to cover larger areas. They're more flexible than traditional ROVs, able to go places where tethers can't reach, yet they can still be directly controlled when necessary. Another area of development is in situ analysis, the ability to analyze samples on the seafloor without bringing them to the surface. Instruments that can measure chemical composition, identify microorganisms, or determine age of rocks, all while still at depth, would revolutionize deep-sea science. Currently, most samples have to be brought to the surface for analysis, and in the process they're exposed to huge changes in pressure and temperature that can alter them. In situ analysis avoids this problem, providing data about the trench as it actually is, not as it appears after being brought to the surface. Advances in imaging technology are also helping. High-definition cameras, 3D imaging systems, and bioluminescent sensitive cameras allow scientists to see the trench in unprecedented detail. These cameras can capture behaviors and organisms that might be missed by human observers, and they can provide data that can be analyzed long after the expedition is over. But perhaps the most important development is not technological but collaborative. The study of the Mariana Trench is increasingly a global effort, with scientists from many countries working together, sharing data, and coordinating expeditions. International collaborations bring together expertise from different fields, from geology to biology to chemistry, and they allow for more comprehensive studies than any single nation or institution could conduct alone. As you rest tonight, think about those explorers, past and present, descending into the trench with cameras and instruments, documenting a world that few will ever see. Think about the engineers designing submersibles and ROVs, pushing the limits of technology to reach the deepest places. Think about the scientists analyzing samples and data, piecing together the story of the trench from fragments and clues. Exploration of the Mariana Trench is one of the last great frontiers on Earth, and we're still in the early stages of understanding what's down there. Every expedition brings new discoveries, new questions, and new appreciation for the complexity and diversity of life on our planet. The trench, as time capsule. The Mariana Trench is not just a habitat for strange creatures and a site of extreme conditions. It's also a geological archive, a place where Earth's history is recorded in rock and sediment, where processes that shape our planet have been operating for millions of years. By studying the trench, scientists can learn about plate tectonics, about the formation of oceanic crust, about the recycling of Earth's surface materials, and even about the planet's deep interior. The rocks exposed on the walls of the Mariana Trench are some of the oldest oceanic crust on Earth. As the Pacific Plate descends into the mantle, it exposes rock that formed up to 170 million years ago. That's Jurassic Age rock, formed at a mid-ocean ridge long since disappeared, carried across the Pacific for millions of years, and now being dragged back down into the Earth. By sampling these rocks, scientists can learn about the conditions under which they formed, the composition of the mantle at that time, and how the Pacific Plate has evolved over its long history. Some of the rock samples collected from the trench are peridotite, a type of rock from the Earth's upper mantle. Normally, mantle rock is buried deep beneath oceanic crust and is inaccessible except where tectonic forces bring it to the surface. In the Mariana Trench region, especially near the Forak and at serpentine mud volcanoes, peridotite is exposed or erupted, providing a rare opportunity to study mantle material directly. These samples reveal the composition of the mantle beneath the Pacific Plate and the chemical changes that occur as the plate is subducted. The sediment at the bottom of the trench is another valuable archive. Layers of sediment accumulate slowly over time, recording changes in ocean conditions, in climate, in biological productivity. By taking sediment cores, long cylinders of sediment extracted from the seafloor, scientists can read this record, layer by layer. Each layer represents a period of time, with older layers deeper down and younger layers near the surface. The composition of the sediment, the types of microfossils it contains, even the magnetic orientation of mineral grains, all provide clues about the past. One interesting finding from sediment cores in the Mariana region is evidence of past volcanic eruptions. Layers of volcanic ash, spread across the seafloor by currents, mark times when nearby volcanoes erupted explosively. By dating these ash layers, scientists can reconstruct the volcanic history of the Mariana Arc, learning when eruptions occurred, how frequently, and how large they were. This information is important for understanding the long-term behavior of subduction zone volcanoes and for assessing volcanic hazards in the region. The trench is also a site of intense seismic activity. Earthquakes occur frequently as the Pacific Plate grinds against the Mariana Plate, building up stress and then releasing it suddenly. Over the past century, hundreds of earthquakes have been recorded in the Mariana region, ranging from small tremors to large events. Some of these earthquakes are shallow, occurring near the surface where the plates first meet. Others are deep, occurring hundreds of kilometers down as the subducted plate continues to sink through the mantle. Studying these earthquakes helps scientists understand how subduction works. By analyzing the location, depth, and magnitude of earthquakes, they can map the shape of the subducting slab, determine how fast it's sinking, and identify zones where stress is accumulating. This information is crucial for assessing earthquake hazards. Subduction zones are capable of producing the largest earthquakes on Earth, magnitude 9 or greater, and these earthquakes can generate devastating tsunamis. The Mariana Trench subduction zone has not produced a major earthquake in recent history, at least not one that caused significant damage, partly because it's far from major population centers. But the absence of recent large earthquakes doesn't mean the zone is inactive. Stress may be accumulating, and a large earthquake could occur in the future. Understanding the seismic behavior of the trench is important for assessing long-term hazards. Tsunamis are another concern. When an earthquake occurs beneath the ocean, it can displace large volumes of water, generating waves that travel across the ocean at high speed. Tsunamis generated by subduction zone earthquakes have caused enormous destruction in the past. The 2011 Tohoku earthquake and tsunami in Japan, which killed nearly 20,000 people and caused the Fukushima nuclear disaster, was generated by a subduction zone not unlike the Mariana Trench. The 2004 Indian Ocean tsunami, which killed over 200,000 people, was also generated by a subduction zone. Scientists study the Mariana Trench to better understand how tsunamis are generated. By examining the seafloor, looking for evidence of past landslides and underwater avalanches, and modeling how water would behave during an earthquake, they can assess the tsunami hazard. Some features of the trench, like steep slopes and unstable sediment, could amplify tsunamis, making them larger and more destructive. Other features might dampen them. Understanding these factors is crucial for preparing coastal communities and developing early warning systems. The subduction process at the Mariana Trench is also part of a much larger system. The global cycle of plate tectonics, oceanic crust is created at mid-ocean ridges, moves across the ocean floor for millions of years, and is eventually subducted at trenches like the Mariana. This cycle recycles Earth's crust, bringing surface materials down into the mantle and returning mantle materials to the surface through volcanism. It's a fundamental process that has been shaping the planet for billions of years. By studying the Mariana Trench, scientists learn about this cycle. They learn how fast subduction occurs, what happens to the subducted material, how long it takes for the slab to sink through the mantle, and whether it reaches the core mantle boundary or gets stuck somewhere along the way. They learn about the release of volatiles, like water and carbon dioxide, from the subducting slab, and how these volatiles affect the mantle above, generating magma and fueling volcanoes. They learn about the return of materials to the surface, completing the cycle. The trench also provides insights into Earth's deep interior. Seismic waves from earthquakes in the Mariana region travel through the mantle and core, and by studying these waves, scientists can image the structure of the deep Earth. They found that the subducted Pacific Plate can be traced down to the mantle transition zone at about 660 kilometers depth, and possibly deeper. Some studies suggest that the slab reaches the core mantle boundary, nearly 3,000 kilometers down. These findings help us understand the dynamics of the mantle, how heat is transported, and how convection drives plate tectonics. One fascinating aspect of subduction zones is that they transport surface materials deep into the Earth. Water, carbon, and other volatile elements are carried down with the subducting plate. Most of these volatiles are released as the plate heats up and are returned to the surface through volcanism. But some may be carried deeper, into the lower mantle, perhaps even to the core mantle boundary. These deep subducted volatiles could influence the chemistry of the mantle, affect the generation of deep plumes, and play a role in long-term planetary evolution. The Mariana Trench, in this sense, is a conduit connecting the surface to the deep interior. It's a place where surface and interior exchange materials and energy, where the slow churning of the mantle becomes visible as earthquakes, volcanoes, and trenches. By studying it, we learn not just about one specific location, but about the fundamental processes that make Earth a dynamic, living planet. As you rest, imagine the trench as a window into deep time, a place where rock formed in the age of dinosaurs is being returned to the mantle. Imagine the slow, patient recycling of the planet's surface, the creation and destruction of ocean floor, the building of volcanoes and the carving of trenches. The Mariana Trench is not just the deepest place on Earth, it's a place where Earth's past, present and future converge, where the forces that have shaped our planet for billions of years are still at work, still carving, still building, still renewing. It's a reminder that our planet is not a static ball of rock but a dynamic, ever-changing system, alive with motion and energy. Closing journey back to surface. We've traveled far tonight, down through zones of light and shadow, past the point where the sun's rays can reach, into the cold and crushing darkness of the Hadal Zone. We've visited the deepest place on Earth, seen the creatures that live there, explored the chemistry of hidden vents, and learned about the forces that carved this great wound in the planet's surface. Now, as you rest, as sleep draws near, it's time to begin the journey back. Imagine yourself rising slowly from the floor of Challenger. Deep, the sediment, smooth and covered in fine ooze, falls away beneath you. The darkness is still absolute, but you feel the weight of pressure beginning to lessen just slightly as you ascend. The temperature remains cold, but you know that higher up the water will warm, degree by slow degree. As you rise, you pass through layers of the trench ecosystem. Amphipods scuttle across rocks. A snailfish glides past, its translucent body barely visible in the faint glow of bioluminescent creatures. Bacterial mats coat the surfaces of rocks, invisible but present, the foundation of everything living here. The trench is alive, more alive than anyone once thought possible, and it continues even as you leave, patient and unchanging. Higher still, you pass the 6,000-meter mark, leaving the Hadal Zone behind. The pressure eases further. Now you're in the abyssal zone, a vast, flat plain that covers more of Earth's surface than all the continents combined. Here too, life exists, adapted to the cold and dark but not to the extremes of the trench. Sea cucumbers dot the sediment, feeding on the slow rain of marine snow. The occasional deep-sea fish drifts past, hunting in the darkness. At 4,000 meters, you enter the bathypelagic pelagic zone, the midnight zone. The water is no longer near freezing. It's slightly warmer, a few degrees Celsius. There's more life here, more diversity. Jellyfish pulse through the water. Squid with enormous eyes scan for prey. Lanternfish migrate up and down through the water column, following the diel vertical migration that brings them to shallower depths at night to feed and back down to safety during the day. At 1,000 meters, the first hints of light appear. Not sunlight, not yet, but bioluminescence becomes more common. Creatures flash and glow, communicating, hunting, or trying to startle predators. This is the twilight zone, a realm of shadows and dim blue light filtering down from above. Life is abundant here, perhaps more abundant than anywhere else in the ocean. Small fish, squid, shrimp, and countless other creatures fill the water, feeding on the rich supply of food drifting down from the surface. And then, at 200 meters, you break into the sunlight zone, and suddenly everything changes. Light floods in, bright and warm. The water is no longer cold, but pleasant, bathed in sunlight. Colors return: the blue of the water, the green of algae, the silver flash of fish. The surface world, so different from the abyss, feels almost unreal after the journey you've taken. You rise the last few meters and break the surface. Air, warm and breathable, surrounds you. The sky stretches overhead, blue or perhaps scattered with clouds. Waves lap gently. In the distance you might see land, or perhaps just the endless expanse of the Pacific Ocean shimmering under the sun. You've returned from the deepest place on Earth, from a realm as alien as any planet, and yet it's all part of the same world, the same ocean that laps at beaches and shores around the globe. The Mariana Trench, for all its strangeness, is part of our planet. It's connected to the surface by currents, by the rain of marine snow, by the slow recycling of Earth's crust. What happens there affects the entire ocean, the entire planet. The microbes breaking down organic matter, the animals adapted to extreme pressure, the geological processes shaping the seafloor, all are part of the intricate web of systems that make Earth unique. We've learned so much about the trench in recent decades, but there's still so much we don't know. Vast areas remain unexplored. New species are discovered on almost every expedition. The chemistry of vent systems, the behavior of microbes under pressure, the long-term geological history of the region, all are subjects of ongoing research. The Mariana Trench holds secrets we haven't even begun to uncover, and future explorers will continue to dive into its depths, seeking answers, driven by curiosity and the desire to understand this remarkable place. Tonight, as you drift into sleep, carry with you the knowledge that Earth still has frontiers, places where wonder and mystery remain. The Mariana Trench is one of those places, a reminder that even on a planet we've explored for millennia, there are still discoveries to be made, still questions to be answered. It's a place that challenges our assumptions about life, about the limits of habitability, about the forces that shape our world. And it's a place that, despite its remoteness, is not immune to human influence. The plastic on the seafloor, the contaminants in the animals, the slow changes in oxygen and temperature, all remind us that our actions have consequences that reach even the deepest places. The trench is not separate from us. It's part of the same system, and what we do to the ocean affects it, just as it affects everywhere else. But tonight, let go of those concerns. Rest in the knowledge that the trench exists, deep and quiet, a place of wonder and resilience. Let your mind drift back down through the zones, past the fish and jellies, past the amphipods and snailfish, down to the very bottom where the sediment is smooth and the darkness is complete. There in that silent world, life persists, adapted and thriving, a testament to the tenacity and creativity of evolution. You've traveled to the deepest place on Earth tonight, not in body but in mind, and in doing so, you've touched something profound. The abyss does not judge, does not hurry, does not change. It simply exists, patient and eternal, waiting for those brave enough or curious enough to seek it out. And whether you dream of deep waters, or of something else entirely, whether sleep finds you now or later, know that the journey has been worth taking. Rest well. The ocean will still be there tomorrow, vast and mysterious. The Mariana Trench lying quiet in its depths, holding secrets and stories that stretch back millions of years. And perhaps in the future, you'll return to explore it again, to learn more, to discover something new in the endless darkness of the abyss below. Good night.